So I wanted to make a short video on ventricular pressure volume loops. Right? So these are PV loops of the left ventricle. You can do them of the right ventricle. Um, Generally, they're done of the left because that, of course, is the ventricle that's doing much more significant uh, work than the right ventricle, even though they move the same amount of blood. So that gets to a point of which, right, the left ventricle does work under a much greater pressure than does the right, right, because the resistances are different of those two circuits. Hopefully that's clear already, right? The pulmonary circuit has much lower resistance and so requires much lower pressure to move the same volume of blood as the left ventricle, right? And again, of course, they have to be equal because the two circuits feed each other, right? Go right back to that very first video where one circuit feeds the other. And so, they have to have the same output. Otherwise, over time, blood would be backing up into one of those circuits, which is generally the pulmonary because it's the low pressure circuit that's got more essentially quote unquote give to it. So anyway, with that said, we've got what we plot in this curve is ventricular volume rising as we go left to right here versus ventricular pressure, right? And what we want to do is we want to basically move around this loop in a counterclockwise fashion, right? But let me point out a couple of things first, right? And what that will entail and we'll get there, but what that would entail moving around this loop counterclockwise was one complete cycle of, in this case, left ventricular performance work. Okay. So if we look at the volume, though, let's start with one of these. If we look at the volume, right, we're going to be going left to right here, right, because we said counterclockwise. And so initially, right, we're going to start on the bottom here. And what we can see, though, is that there are 2 points at which the volume here and here, right, where the volume stays the same, right? That would be where the volume is fixed, but the pressure is changing, right? Because we're either going up, right? On this side, we're going up. On this side, we're going down, right? And so those are the points where we are isovolumic, right? And they're already labeled here. Relaxing when our pressure is falling, and isovolumic contraction when our pressure is rising. Now, if you think about it, that means the valves, if you're isovolumic, that means the volume's not changing. Iso means same, right? Which means all the valves are closed, okay? Which means to move in or out of those phases is when the valves are opening and closing, right? So as you'll see, the change in the valve positions is occurring at the quote unquote corners of the pressure volume loop. Okay, now once we see what we're talking about here, it'll make perfect sense, hopefully, right? But so let's pick a spot here, right? So if we start down here at the very bottom, right, bottom left corner, we have our lowest volume, so that would be our end systolic volume, right? And our volume is about to start increasing, right? We're about to start to moving left to right, which is increase in ventricular volume. And so the AV valve opens to allow the ventricular volume to increase. Okay, so our volume rising, and that will start, if you go back to your ventricular volume trace, right, not shown here, but that starts with passive filling. I could sketch it down here real quickly, right? Passive filling, then active filling, then isovolumic, then ejecting, and then passive relaxation, and then we start all over again, right? So that's the ventricular volume trace, right? Which you should have seen before. But ventricular volume rises first with passive filling, then with active filling. Pressure is going to rise a little bit during active filling just because it becomes more full and starts to stretch those walls, pressure rising. Then we're at our EDV, our end diastolic volume, right? We're about to start contracting, right? Because we see our pressure is about to start going up. And so we start our systolic phase, right? And as soon as that happens, the AV valves close. right? So we have our isovolumic contraction, pressure rises until we can open up the semilunar valve. Here it is, opening, and start ejecting blood, right? And as we eject blood, of course, the volume falls. So we have to start moving back to the left here, right? So this is all ejection as blood is leaving the ventricle, right? And initially the pressure rises because the ventricle keeps contracting harder and harder. And then the ventricle starts to relax a little bit, but it's still not enough that it's not still ejecting, right? And there's some inertia that involved there as well. But when we stop ejecting, right, when the ventricular pressure falls enough, then our semilunar valve closes, right? Basically, aortic blood starts to flow backwards for a split second, slamming that semilunar valve, that aortic valve shut, and opposing backwards flow into the heart, which of course we don't want. But we can't start immediately refilling with blood, right? We have to drop our pressure. So there's our isovolumic relaxation again, all the way back down to where the AV valves open and we start to passively fill from the veins again, right? And so we have this complete cycle. So all sorts of things will pop up as apparent on here, right? First of all, hopefully we can march through the cardiac cycle just by following that loop that we just went through. But remember, the difference between EDV, maximum volume, and minimum volume, ESV, is the stroke volume, right? And so that's just the width of the curve, right? That's telling us how much volume we move per contraction, stroke volume. Another thing we can see is we can see our peak, right, when we're at peak ventricular pressure, the semilunar valve is open. And so aortic pressure and ventricular pressure are the same. There's no door closed in between the two. They're continuous. And so we get our systolic pressure, right, at that peak there. Now, right before the semilunar opened, the aortic pressure was at its lowest value, right? And so that value over here would be our minimum pressure, right, or the diastolic pressure. Well, the difference between the two is the pulse pressure. We could even do mean arterial pressure from this, right? Mean arterial pressure is it's 1/3 of the pulse pressure plus the diastolic pressure. We can get into why it's 1/3, right? But the mean pressure is going to be somewhere between these two. It just doesn't happen to be halfway in between, right? Because we spend more time in systole than diastole, which you can actually see here, right? Because we spend more time at higher pressure, right? Like sort of above this halfway line than we do below that halfway line between systolic and diastolic, right? We spend more time above than below. And so the mean is actually, more time below. You can't see it graphically on here. More time below, I should say, than above, which you can't see on this graph because there's no time component on this graph. But that means that our mean pressure is about 1/3 of the way up. Right? It'd actually be about here. Okay, and again, separate discussion. Okay, so last thing, right? In fluid dynamics, work done is actually pressure times the volume moved, right? In other words, it's the volume you move at a given pressure, right? Well, we just said we could get a pressure. We could take an average of this portion of the trace right here, basically. Right? That's again, over here, pressure, right? And then multiply it by the volume, right? So stroke volume times essentially the height. It's not a perfect square or rectangle here. So we have to use a mean for this top curve, essentially. But that area would equal or be proportional to the work performed, right? And the work performed is also indicative of the amount of oxygen that's consumed, right? The amount of contractile work the cells are doing would determine how much oxygen they consume. And so the area of the curve actually tells us something, right? It tells us about how much O2 is being consumed, as well as how much work is done. Now, there's pressure work and there's volume work, right? Because there's those two components. We want your heart to be doing lots of volume work at the lowest pressure possible, right? Um, basically saying it's easy to move a lot of volume without having to squeeze the blood too hard, right? And so we actually want a square, a loop, if you will, um, that's sort of short and squat as opposed to tall and skinny, right? Those two could have the same area, but one would move a smaller, the tall skinny one would move a smaller volume, right? So let's look at that, right? Because one of the things we know about the heart is that it's dynamic, right? And so these, EDV and ESV can change. The blood pressure, the pressure that's required to overcome to open that semilunar valve could change, right? And so, right, this could move up, right? All kinds of things could change, right? We could fill to a greater degree that would move us this way, and so the key thing about the loop is it's dynamic. Now, what's the most important thing is understanding the loop dynamics, like in a situation. But we also want to understand that, we've got this normal loop here, which I'm going to highlight, try to highlight, right? This is our normal. Sorry, I'm not trying very straight lines here, right? But we've got this dashed line that's this altered loop. Well, what's changed here? Well, we've got increased filling, right? In other words, our ventricular volume is going to rise to this greater degree, all the way over to here, right? And one way that could happen is if we allowed more filling time, right? More filling time at a lower heart rate, for instance, right? Well, just because your heart rate is lower doesn't mean we need less cardiac output. So watch how this is compensated. The more you fill, right, we have to go through our isovolumic phase, right, to get our semilunar open. But then look what happens. The more you fill, the harder you're going to contract, right? So your pressures are actually higher, and your more blood you're going to move, right? You have this increase in stroke volume, right? That's Starling's law of the heart, right? Increased stretch means an increase in optimal overlap of thick and thin filaments, a harder contraction, which is going to A, increase the pressure generated, but B, it's going to move more blood, right? We're going to contract harder and eject more of that blood that actually came in and filled the heart. So whatever leads to increased filling, be it exercise and the muscular pump that's squeezing blood back to the heart, or just a lower heart rate, a higher blood volume, lots of things can lead to increased venous return to the heart that would lead to the Starling mechanism and an increase in stroke volume that, of course, is right. And remember that cardiac output equals, um, sorry, equals heart rate times stroke volume. So if heart rate stays the same and stroke volume were to go up, then our cardiac output would go up, right? And then, of course, remember that blood pressure, right, equals cardiac output times resistance. And so we just said cardiac output goes up, which means our blood pressure is going to go up. Aha, right? Remember, this is our peak systolic pressure, right? We report your blood pressure as systolic over diastolic, right? And your systolic and diastolic pressures just changed, in this case, increasing for the reasons we just pointed out. All right, one more example here. On the bottom right here, we've got here's our normal trace again. I won't trace the whole thing, but this guy, maybe I will trace the whole thing. Right? Here's normal, all wiggly. But now what's happening is we've increased the arterial pressure, right? In other words, you're hypertensive. And so what happens is it's harder to open the door to eject blood. It's harder to open the semilunar valve. And so our isovolumic phase has to get longer, right? We have to squeeze harder, higher pressure, to get that door to open. Well, that means we spend more time in the isovolumic phases, right? Because we have to rise to a higher pressure and we have to fall from a higher pressure, which means you spend less time in the ejection phase, right? So there's less time ejecting, right? We still, right? We still contract and we still eject. Oh, we better, right? But we spend less time there, and so our stroke volume actually falls, right? And that's bad, right? Because we're now in this scenario, we're doing, right? This blue loop has a very similar area, maybe even greater area than the red loop, right? Remember we said that that correlates with the amount of work and the amount of oxygen consumed. So you're actually consuming as much or more oxygen, but you're moving less blood, right? Your stroke volume fell. Remember, up here to your cardiac output. If stroke volume falls, then your cardiac output falls. Okay? So we have a problem now, right? Because you're doing more pressure work and less volume work when you're hypertensive, or at least potentially. Now, are there compensatory mechanisms? Sure, there are, right? To oppose your hypertension and to improve your cardiac performance even when you're hypertensive. But it does point to the idea that hypertension is very dangerous in people with weakened hearts, right? So think old people, right? Old and unfit people or people with cardiovascular disease, right? Because if you think about it, their heart is weaker. If they have hypertension on top of that, then you basically what you're saying to the heart is, oh, you're weak and sick, but we're going to make you work harder. It kind of doesn't add up, right? And they end up with heart failure, where the heart can't perform to the degree required to overcome their blood pressure and move blood into the vascular circuits, right? And so they end up with reduced cardiac output and potentially lots of other problems that stem from that. Okay, so those are our pressure volume loops, right? We should understand the basics of what that loop is showing us, right? In terms of stroke volume, in terms of the blood pressure, the systolic and diastolic, but also, when we get changes to the shape of the loop, what that means, right? With, for instance, the Starling effect up here at the top, right, where we had increased filling, and how that's actually, potentially a good thing because we're moving more blood at not much greater pressure. And then bad when we have hypertension down here, increase in afterload, right? Remember, this is preload, right? The increased filling is preload. The increase in blood pressure, though, is afterload, and we can see how that's bad because we end up doing more pressure work and less volume work, right? Okay, there you go.